Okay, so yesterday we finished up talking about the Vant-Hoff equation, which relates Gibbs free energy change to equilibrium constants, and we looked at an example here. We said, what if delta G for a reaction is 0? What is KEQ? And we can plug that into the Vant-Hoff equation, and we said that that equals 1, which means the ratio of products to reactants is going to be equal. So if we think about this reaction coordinate diagram, it's an equal hump. If you let this run over time, it doesn't really have a preference for the starting material side or product side, so it's going to evenly distribute between both of those. But let's take a harder example now. What if delta G is negative 20 kilojoules per mole? And then I'm going to write assume a temperature. And we're going to do 298 Kelvin. That's about 25 Celsius. So what percent of the reaction will be product at equilibrium? So I'll give you guys a minute to work on this, but I would check with your neighbor and make sure that all your units are canceling correctly. And I'll rewrite the equation that you need over here. What percentage of the reaction will be product? I just abbreviated product. Yeah, that's a good question. What does R stand for in these types of equations?
The natural gas constant.
Yeah, gas constants. Does anybody remember what that is?
8.314.
8.314 joules per mole Kelvin. So let's start working through this together, and I'll show you guys a mistake that oftentimes people make. We'll say, all right, KEQ in this case must be equal to negative 20 kilojoules per mole. Oops, I'm forgetting my E. Over negative 8.314 joules per mole Kelvin times temperature, which we said is 298 K. Are we done there? Do we just plug it in? What's wrong? Yeah, joules aren't in the same unit, right? We've got kilojoules on the top, but only joules on the bottom. So all I'm going to do is multiply this by a conversion factor. I'm going to say, all right, 1 kilojoule is equal to 1,000 joules, right? All right, so who wants to help me with this calculator work?
3204.8.
3204.8, all right. I'll just round this to 3205. That's close enough for government work. All right. Does this have units? Nope. It's unitless, right? It's just a ratio. So going back to that original question, we said what percent of the reaction will be product at equilibrium? Well, it's not going to be 3,205. We have to convert this back into a percentage unit. So I'll show you guys how I would go about doing this. I would say, all right, KEQ we know is equal to the concentration of products over the concentration of reactants. And we know that this is equal to 3205, right? Another way of writing this would be to say, all right, this is equal to products over reactants is equal to 3205 over 1, right? So that means we've got over 3,000 times as much of our products as we do of our reactants at this point. But let's try to convert this into a percentage. Okay, so for this, what I'm going to do is I'm going to say, all right, to find our percentage, we want to take our products divided by the sum of our products plus our reactants times 100, and that will give you the percent of the equilibrium that is your product. So what do you guys think it would be in this case?
99.97.
Yeah, so let's plug this in. So product, we know is going to be this numerator value because it's equal. So all I'm going to do is say, all right, product is 3205. We know product down here is also going to be 3205. And then our reactant, what would that be? 1. So I'm going to plug that in, and I'm going to say times 100. And that gives us what? 99.97%. Perfect. This gets back to the idea of what an equilibrium is, though. Usually, if a reaction's 99.97% on the product side, we don't really consider that an equilibrium anymore. Theoretically, every reaction is at equilibrium, but the way we show that arrow as either a double-headed arrow or a single-headed arrow depends a lot on this. If we're talking about something that's 99.97, it's essentially all product at that point. So this is basically non-equilibrium conditions. So let's make a note of that. When delta G is less than negative 20 kilojoules per mole, the reaction is essentially a one-way arrow. In theory, we could say it is at equilibrium, but in practice, we know if something's 99.97% on the product side, it's essentially a one-way reaction, not a reversible one. Yep?
How do you know that the reactance is 1?
Yeah, so it's just a ratio up here, right? So you were wondering, how do we know the reactants are 1? All I did was convert this to a ratio. We know it's a ratio of 3205 over 1. That's our ratio. And then all I did was plug those ratio numbers in. That was all I was doing, was just a simple mathematical manipulation.
So in the reaction, numbers be different than what came before that?
No, all I was doing was saying this part up here is the exact same as this, right? So I just divided it into a numerator and denominator so that I could say, all right, the product ratio or product to reactant ratio is the same as 3205 to 1. That's all it was. Yeah. All right. So in general, if you ever see a reaction that has a really big drop in delta G, you can consider it non-equilibrium conditions, even though you could theoretically make the argument it is still under equilibrium conditions. Make sense? A little bit weird to think about. The same is true for acid-base reactions. If you remember going to acid-base reactions, we had a lot of equilibrium arrows. But I said with a strong acid or a strong base, quite often those equilibrium arrows aren't really equilibrium arrows. They're almost exclusively on one side or the other. This is kind of fitting into that same idea. All right. So going back up to this reaction coordinate diagram. Do you think this reaction is going to occur quickly? Or do we not know? What are we missing in that reaction coordinate diagram? Activation energy, right? So we've got two components to all reactions. Activation energy is oftentimes written as EA, where A is a subscript, and it basically tells you how big that energetic barrier is that you have to overcome in order for the reaction to proceed. This really determines the reaction rate. So let's talk about what influences that EA, or activation energy. And let's make a note, a spontaneous reaction does not always occur quickly. So like I said yesterday, I'm spontaneously transforming into carbon dioxide and water, but hopefully not very quickly. I'm hoping to get another, 50, 60 years out of this. So it's important to realize that, right? Things can be spontaneous but not be happening quickly. So let's think about reaction rates. How many of you remember reaction rates from Gen Chem? A couple people? So rate equations. You could say a rate can be determined by little k, that's our rate constant, times a concentration of one of our reactants. So remember, anytime I show something in brackets, that's referring to concentration. So this is our rate constant. There's a few different things that are factored into rate constants, and we'll talk about that in a second. And then this is the concentration of our reactant. Why do you think concentration matters when we're talking about rate? Yeah, it's a little bit weird to think about too, but if you think about a reaction, all it is a bunch of molecules bumping into one another. And when they bump into one another, they react. If you've got a really low concentration, the probability of one molecule finding another one to react with goes down pretty quickly. But if it's at high concentration, they're going to be in close proximity and bump into each other a lot more. That increases the reaction rate. So let's talk about that briefly. When you increase concentration, you increase the frequency of molecular collisions. This means that you end up having a faster rate. So concentration is hugely important. So let's talk a bit about that reactant portion of the equation, and then we'll go back to the rate constant part. You could have a reaction where you have a rate equals to K, and then I'll call this reactant A. So it's only dependent on the concentration of A. You could have something that looks like this, where rate is equal to a rate constant, and then you need A to collide with B. Or you could have something where you say, you know, maybe we just need two A molecules to come together and collide. However, normally if people write this out, they'll write this in the mathematical term and they'll just say Ka squared, right? It's the same thing, but it relies on two molecules colliding with one another, where the first one was just one molecule of itself reacting. And then last but not least, you might run into some others that look like this. Maybe you rely on two A's colliding with a B. So I'll say A squared B. And we can classify these as first, second, or third order reactions. The first order reaction would be the example on the left, meaning it only relies on one thing, either decomposing or reacting. A second order means it relies on two molecules colliding, either two molecules that are identical or different. And then a third order means it relies on three things colliding. Does that make sense? Easiest thing you can do with this is just add together the exponents for all of the different reagents, right? So in this case, you could say, oh, A is raised to the 1 power, so that's a first order. Over here, we've got 1 plus 1, so that's second order. Or you could say, hey, that's a 2, that's second order. Over here, we've got 2 plus 1, so that's a third order. So you can really quickly add together all of those exponent values to find the rate order for a reaction. Quite often, students will ask me, what about fourth or fifth or sixth orders? Does anybody know about those? They really are super duper rare, to the point where they're not even worth talking about. The probability of a reaction relying on 4 molecules colliding at one point in time is incredibly low, right? So normally we only deal with first and second order, occasionally third order, and I honestly have never seen a fourth or fifth order reaction before. So let's write down the reaction order is the sum of the exponents. The other thing, too, is if you think about the rate of a reaction, the units depend a lot on whether or not it's first, second, or third order, right? Because in these, we've got concentration units that are usually done in molar, but some of these are first order, so you'd only have molar. The second order ones would be molar squared, right? And then the third order, you'd have molar cubed. So you do have different rates depending on whether it's first, second, or third ordered. So let's take a look at an example reaction, and I want you guys to help me determine whether or not it's first, second, or third order. All right, so for this example reaction, we've got this compound. It's an alkyl halide. You can even name it if you want. What would this be called? Not everybody all at once. Longest carbon chain. V1, 2, 3. Looks like we've got a methyl group over here and an iodine over here. What would go first, iodine or the methyl? So this would be 2 iodo, 2 methyl, propane. So just practice your naming, make sure you got that down. Then we're going to react this with a sulfur that has a negative charge. And we know that the products from this reaction involve a new covalent bond. And then iodine pops off like that. Okay, experimentally, we have to determine whether or not this is first, second, or third order. And so what this chemist decided to do was change the rates of things. So let's make some notes about what this scientist did. First thing the scientist did was he doubled the rate, or she doubled the rate of the sulfur compound, or doubled the concentration. But this has no effect. All right. The next test that this chemist did was double the rate of the other, or double the concentration of the other one. So I'll just write the other reagent in here. And the rate doubles. All right, so first what we need to do is to determine what the rate equation would be for this reaction. What do you guys think it should be? We don't know what the little k is, but what should we include? Should we include the sulfur component, the alkyl halide component, or both? Just the alkyl halide. It's the only one that actually factors into the rate. We know changing the concentration of the sulfur reagent really doesn't do anything. So the rate is only dependent on this reagent. So what order reaction must this be? Okay, so this must be a first order reaction. In fact, this is a reaction that we're going to cover in, I believe, the next chapter. This is a substitution reaction, so you see how we substituted iodine for something else? And what this is called is a first order substitution reaction. Makes sense? So people call this SN1. The S means substitution. The N means it's a nucleophile doing the substitution, and we'll talk about what a nucleophile is later. And then 1 means first order reaction. As you can imagine, there are probably other substitution reactions where the order isn't first order, and those are classified as SN2 reactions, so you can have a second order substitution. We're not going to get into that now, but I did want to show you guys an example of how this applies to next chapter. So concentration can be used to figure out the reaction rates and whether or not a reaction is first, second, or third order, but we haven't talked at all about that little k, the rate constant. So let's get into that. So what about little k? the rate constant. And make sure you write that as a lowercase k, not a capital K. That means something entirely different. So what can impact K? Who remembers from Gen Chem? There's one huge thing. What else can increase the rate of molecular collisions besides concentration? Temperature, right? If you increase temperature, molecules move around faster and will bump into each other more. So temperature can change the frequency of collisions. So in general, if a reaction is spontaneous, increasing something by 10 degrees will double the rate. It's a really good rule of thumb. So let's write that down. Rule of thumb. Whoop. Increase of 10 degrees, whoa, that's messy, will double your rate. So that's one big component. There's also a second component, right? If you're thinking about two molecules hitting one another, they have to be hitting each other the right way, right? So they have to be striking each other in a way that allows the reaction to occur. And so orientation is a big one. So let's talk about that. And I'm going to put in a new word here called sterics. So what sterics means is how accessible is the reactive site on your molecule, right? Sometimes it's really easy to access the reactive site on a molecule. Other times it's kind of hidden and tucked away and harder for the other reagent to strike into that reactive site. Yep.
Does that have anything to do with allosteric sites?
It's similar. That's getting more into biochemistry though. Yeah. So sterics basically refers to how bulky is your molecule. If it's really, really bulky and it's hard to access that reactive site, your rate's going to go down tremendously. So bulky molecules are a lot less reactive in general. But let's write this in plain English. So that's a big component. And then last but not least is just the activation energy in general. So activation energy does have pressure factored into it. So let's talk about activation energy. And activation energy is essentially asking how easy is it to make or break those bonds. So these are the three main components. Temperature increases the frequency of collision. Orientation or sterics can also impact how frequent the molecules collide with one another. And then activation energy says, all right, how much energy do you need in that collision in order for the reaction to actually occur? So all three of these are hugely important. However, there are some situations where your activation energy is just super duper high. That means your reaction is going to be slow. If you're a chemist and you're running into that sort of situation, what might be a useful trick for getting that reaction to occur? Catalysts, right? You guys remember talking about those? So I'll call this a trick to get around large EAs. And this is use a catalyst. And it's important to note that catalysts don't exactly lower the EA of the existing reaction. It allows the reaction to go through a completely different pathway. And this is something that confuses people in Gen Chem. They think a catalyst just magically lowers the activation energy for an existing pathway. Not exactly. It finds an alternate route to get from starting material to products. And I'll show you guys what that looks like with the reaction coordinate diagram. So let's think about this in terms of our reaction down here. We've got G over here, and our old pathway maybe was like this with a giant hump. That was way too hard for us to get over. What a catalyst will do is it'll say, let's not go along that black pathway, let's blaze our own trail. And maybe I'm going to do something like that. So I'm going to go through a couple different intermediates or a couple different transition states for this one. So what would the activation energy be for that blue line? There's a couple things we could look at. We could say, well, maybe it's this hump. Or maybe it's this hump over here to the right. Which one do you think is the true activation energy? You could say both of them are, but what's the realistic one? What's the one slowing us down the most? The bigger hump, right? So we do have two humps to overcome, but this is now our new activation energy. So we'll say new pathway has a much lower activation energy. So we actually did a reaction already in lab that had a catalyst. What was that reaction? Give you a hint. It was the ethanol lab. What was our catalyst for making ethanol? Yeast. So it doesn't have to be a true chemical catalyst. Oftentimes it could be a living organism acting as your catalyst too. And all the yeast did was help us find a new pathway to convert sugar to ethanol. Does that make sense? Okay. So now I've got more of an abstract one for you guys. How many of you grabbed the in-class activity up here? If you haven't, come up and grab it, and then work with a partner. And what I want you guys to think about is, let's say you're in this intermediate well right here. How could you favor formation of product 2 over product 1? And how could you favor formation of product 1 over product 2? So I'll give you guys a minute to think about that. All right, so looking at this, we had a few ideas floating around. A lot of people were trying to throw in catalysts and things like that. You don't need to get that fancy. You can just change temperature, right? And if we think about formation of product 2 over product 1, product 2 is more stable, right? The key thing with this reaction, though, is you have to overcome a larger energetic barrier. To overcome that larger energetic barrier, just crank up the heat, right? And then you can get over that larger activation energy. So crank up the heat would be the right answer here. All right, and that would definitely favor formation of the most stable product. And what this is referred to is the thermodynamic product. And the thermodynamic product is the most stable product. Does that make sense? So for the first question, it's pretty straightforward. Question 2 is a little bit trickier, though, where it says, how might we be able to favor formation of product 1 over product 2? Product 1, if we look at it, is less stable. It's over here, but it's got a smaller hump. And what were you saying again, Cody?
So you have to add enough energy to get over activation energy 1, but not so much that you go over activation energy 2.
Yeah, that's a perfect explanation. So Cody was saying you have to add enough temperature so that you can get over that activation energy 1, but not so much that you can also get over activation energy 2. So for this reaction, for forming product 1, we actually want to run it at lower temperature. The kinetic product in this case is the product with the lowest activation energy. Yep. Oh, I wrote connect. So a kinetic product is a product with the lower activation energy. And let's make a note here that the kinetic product is not always the most stable product. This is the weird thing in organic chemistry that shows up over and over again, is you might have two different reaction pathways. One favors the thermodynamic product and one favors the kinetic product. And you can control which of the two you get by which temperature you run your reaction at. High temperatures always favors the most stable product. When you run things at a lower temperature, then you have to pay close attention to the activation energy for each reaction pathway. It'll favor the formation of the product that has the lower activation energy. Does that make sense? This is weird and a hard concept to wrap your head around, so I got a video that I think helps explain it a little bit better. It's not a cat video, unfortunately. That would be fantastic if I could find one. Let me know if you do. So you can see right here, we've got reactant, or product 1 on the far left, product 2 on the right. We've got these different barriers. So this is EA2, this is EA1, it's a little bit smaller, and right now we're stuck in the middle. And what this person did was they put it on a speaker. The speaker will bounce around as it vibrates. And let's take a look at what happens as we apply our energy to this reaction. So you can see all the reactants. In this case, it's kind of a statistical game, right? So this is at low temperature. It prefers to go over the smaller barrier over the larger barrier. That's not to say you don't get any of it going to the right-hand side. It's just statistically it's more likely to go to the left-hand side. So you can keep on running this, keep on running this, keep on running this, and I'm just going to slide this over. And eventually you end up with almost all of your product as the kinetic product in this case. It's not at the most stable energy state, but it's just the most accessible energy state. Does that make sense? So let's take a look at the other example. And for the other example, we're going to crank up the heat a bit more, but you'll see what this transition looks like. Whoop. So you can see if you really crank up the temperature, your product will actually go to the kinetic product first. But over time, do you see how the kinetic product is actually jumping back into that intermediate well? And then it has enough energy to go over to that thermodynamic product side. And then what happens when it's in that thermodynamic product side? It's stuck. It can't get out anymore. So quite often when chemists describe these reactions, they call them a thermodynamic well, right? Because if you fall in a well, good luck getting out. So it's the same thing with these products. It's not that it doesn't go to the kinetic products. It's that it does, but can go back and then ultimately ends up in that thermodynamic product side. This is the idea of something called microscopic reversibility, that you can oftentimes go back and forth for a reaction, just like we saw in Equilibria reactions. It really does depend on that delta G, though. If the delta G is large enough, like we said, ultimately it's a one-way arrow and it can't get back out of that well anymore. Does that make sense? I know this is a lot of new concepts kind of tied in together. So let's get rid of that. And let's talk about some more complicated stuff. So far we've been looking at really simple reactions where you just have one hump. Reality is not that nice a lot of times. Quite often you might have a reaction where you're going from A to B and then from B to C. So let's try to draw a reaction coordinate diagram for this. We've got G over here, and I'm just going to write reaction progress down here. And I'm going to say, all right, my A starting materials are down here. And my B starting materials, I'm just going to pick one. I'm going to put it up here. Which one's more stable, A or B? A. Okay. So if we think about this, A is more stable. We've got to have some sort of activation energy, so there's going to be a hump in between the two. And then let's say C is down here. Again, you must have an activation energy going from B to C. So I'm going to just draw this as a small hump like that. In fact, I'm going to exaggerate this one a bit more. There we go. So the reaction going from A to B, is that spontaneous or non-spontaneous? Non-spontaneous. But the overall reaction going from A to C, is that spontaneous? Yeah, definitely. We've got a drop in energy there. So let's take a look at this. Over here, we've got this hump. And I'm going to call this EA1. And then over here, we've got another barrier that we have to overcome to get from B to C. And I'll call this EA2. What do you think is going to be rate limiting? Overcoming EA1 or overcoming EA2? EA1, it's a much bigger hill you have to overcome. So EA1, is rate limiting since it is a larger hump. In fact, it is really the thing we look at when we're looking at the rate constant. We really don't care about EA2 because it's negligible compared to EA1. We also have a couple of other things we need to pay attention to in this reaction, specifically at the top of the humps. Up here, we've got what we call a transition state. And to show a transition state, oftentimes you've got this double dagger through here. And this is the transition state. Going from A to B. So what do you think that means, a transition state? Yeah, it's kind of halfway between A and B, right? So it's where bonds are being made and broken. So we're halfway between making a bond, halfway between breaking a bond. So it's that halfway point that's really high energy. Over here, we also have another transition state. Where we're halfway between B and C. We're making and breaking bonds in that process. And then in between here, we've got B, smack in the center, all alone. Is B a transition state? No, it's an intermediate in this case. So I'll make a note. B is an intermediate. So let's think about this. Can you isolate an intermediate? Potentially. It's in its own little well there, so we could isolate it. Could you isolate a transition state? No, it's too energetically unstable. It wants to immediately go down back to B or A. It's not happy at the top of one of those hills. So let's make a note of that. So transition states cannot be isolated. And let's make a note that their bonds are being made and broken. However, we can isolate intermediates. It's a little bit tricky isolating intermediates. Oftentimes it requires fairly advanced instrumentation because, like I said, if we look at B, it's pretty unstable. It wants to get to C as quickly as possible, but using spectroscopy, you might actually be able to observe that intermediate as it exists. It's a lot harder to see a transition state, let alone isolate it.